Hello everyone, and thank you for joining us today. We're excited to present our work titled Bridging the Gap in Health Literacy and Harnessing the Power of Large Language Models to Generate Plain Language Summaries from Biomedical Tests. My name is Felipe Arias Rusi, and I'm joined by my colleagues Carolina Salazar Lara and Ruben Manrique. And our primary objective is to utilize natural language processing along with large language models to translate and complex biomedical tests from their technical language into plain language, and also understand the difference between the linguistic difference between those. By doing this, we aim to reduce inequalities in access to health information and ultimately improve health outcomes for patients. To understand this work, let's first discuss health outcomes. Health outcomes measure the impact of medical interventions, such as a patient's recovery post-transplant. Research shows only 20% of these outcomes stem directly from clinical care. The remaining 80% are shaped by socioeconomic factors, environment, and health literacy. Health literacy is the ability to access, understand, and use health information to make informed decisions. This includes navigating complex healthcare systems, interpreting medical advice, and applying knowledge effectively. Surprisingly, 9 out of 10 people have difficulties understanding health-related medical documentation. Moreover, health literacy has been identified as a contributing factor to health disparities. People from disadvantaged socioeconomic backgrounds and minority populations are more likely to have low health literacy. This highlights the urgent need for effective communication strategies that can bridge these gaps. Accordingly to the World Health Organization, health literacy has been shown to be one of the strongest predictors of health status, along with age, income, employment status, education level, and race. One key strategy to tackle these challenges is plain language. That means health information that's clear, concise, and free of technical language, and it is easy to understand for a layperson. But why does this matter? Because when people actually understand their health, they can make better decisions. But here's the catch. Translating complex science into plain language, it's simple. It takes skilled writers, experts in the field, who also know how to simplify without losing accuracy. And that process is time consuming, and the real test is making sure patients truly get it. So we had 4 main objectives. First, we build one biomedical corpus from different sources like Pfizer, clinical trials, Cochrane, and also we optimize an LLM framework to generate plain language summaries. We also achieve a high accuracy classifier to difference between a plain language test and a technical one. And we did a multi-dimensional evaluation with a combination of computational metrics and also human expertise to evaluate models. To understand better our workflow, we started by obtaining tests with web scraping and then cleaning the test. After that, it is divided into 2 branches. The first branch is about optimizing and training the ML models, and the other is about the generating plain language using LLMs, and also evaluating these LLMs generated tests. Our biomedical corpus is built from 4 main sources. First, we have the clinical trials API, which allows you to retrieve hundreds of thousands of medical trials from the National Library of Medicine. Second, Cochrane offers medical abstracts from various studies, including their respective plain language summaries. On the other hand, Pfizer also has plain language study result summaries for specific studies with technical versions available through the clinical trials API. Finally, trial summaries consist of plain language summaries from diverse companies, making this corpus quite diverse. So, as we mentioned in the workflow, we obtained the test with scrapping, and then we clean the test for processing errors with AI or different tools, mainly PDFs. They used to have grammar errors or things when you try to process the PDF. Also, we then augmented the dataset by cumulative sequential test generation, and then we got an augmented dataset about 23,000 tests. We wanted to understand the linguistic difference between a plain test and a technical one. So we decided to train the models using numerical vectors with relevant linguistic features. We use spacing reliability libraries to obtain things like parts of speech, like amount of nouns, or we can also obtain the amount of date mentions, and we can also compute the reliability metrics like flesh kinket weight level that we also use to evaluate the LLMs generated tests. And after doing some typical data analysis, we obtain 64 variables, and we then did standardized numerical vectors. So we decided to train two kind of models, and after testing them, our best model got a 97% of accuracy in F1 score, and to avoid some kind of bias with the models due to the nature of their train set, we test them with the PLFS plus eLife validation dataset from the violation contest, and we got pretty decent results, like 95% of accuracy and 90 in F1 score. So we decided to keep these models, and then we went for the prompt elaboration part. We analyzed the linguistic attributes also using the data analysis from our corpus, and we identify some main characteristics for plain language summaries, the PLS. We also use EU CTR suggested for specific structures and content for lay protocol synopsis. So depending on the task, in this case is a protocol plain language summary, PPLS, we're going to have different prompts. In this case, it consists in 4 parts: context, structure, content and rules, and also restrictions. But if we wanted to translate an abstract from Cochrane, it would be different. And we did a different prompt for that task, but we won't show it here. But we need to evaluate how the LLMs performs the task of translating translating a text to plain language summary. So we identify 2 primary evaluation approaches. The first is a qualitative assessment supervised by literacy experts who manually review and validate each text. But however, due to the scalability limitations in manual verification, we supplemented this with a quantitative evaluation, leveraging also Cochrane's extensive repository of run-through data. This automated approach enables large-scale analysis and consists of 3 components, based also in the violation contest. Relevance, measure using bear score. Factuality, measure via line score. And reliability, evaluated with metrics such as flash kink, a grade level that I mentioned before. So we selected randomly 300 technical abstracts and generated 300 plain languages version per model. And first, for the Cochrane library, we use a different prompt, as I mentioned before. And for the study protocol, we use the prompt I showed before. But in this case, due to the low scalability, we only did it for 9 protocols because it has to be reviewed manually. So, and for the quantitative evaluation, we got some interesting results. For example, Gemini 1.5 performs very well at the moment of translating a test in plain language, but we can also see that it's even worse than the local models in terms of actuality. So that's very interesting. And in terms of classification, the worst model is DeepSeek R17B, because it is a local model running in a regular GPU. That's also a limitation. And okay, that happens the same with Llama 3.2. For the qualitative evaluation, we only test the generation for 2 models, GPT 3.5 and GPT 4. And we divided it into 4 parts: accuracy, readability, completeness, and usefulness. It is similar than the computational, but this is in a scale of 1 to 5. And we got the following results. For example, we see that GPT-4 performs well, better than GPT 3.5. And not only that, but we can also say that because of the high GPT-4 score, a tool can be useful in the context of translating text into plain language. The conclusion is that we achieve a functional framework developed and successfully integrated data, classification, LLMs, and different tasks, and evaluation for the PLS generation. Also, we achieve accurate classifier with detailed prompts and capable LLMs, especially the API ones that performs better than the local ones. Also, we had significant findings. For example, LLMs can produce high quality PLS that are readable, factual, and relevant. And GPT-4 excels potentially in reliable first drafts. So we recognize current limitations, including some dataset bias, primarily Cochrane sources, limited human review, a fairly narrow qualitative evaluation, and the usual resource constraints. Constraints about, for example, running local LLMs, for example, or limited API keys or API resources to use the OpenAI API, for example. To address this, our future will focus on enhancing and diversifying the dataset. Also, advancing prompting methods like chain of thought and exploring more powerful open source models, for example.